And thank you also to John and Cody for organizing this nice seminar and for giving me the opportunity to speak to you today. So I'm going to be presenting work with Moritz Kahle, with Hans-Peter Nilles, Saul Ramos-Sanchez, and Patrick Mondremanche. And so my motivation is quite quick and easily told. So while a lot of effort is put into providing gauge symmetries for low energy theories from string theory, at least compared to that amount, only a little has been done for providing a flavor or a horizontal symmetry from string theory. So we're talking about a symmetry that acts across the 3 generations of the standard model. And this is why I think there is still a lot to explore in this direction. This is why I'm doing that. So this is the outline of my talk. For this talk in this string pheno seminar series, I thought I'd go from string to pheno. I'm going to start with explaining you my string setup really quickly. We're then going to see how to get a flavor symmetry out of that particular setup. I'm going to tell you a bit of what are possible flavor symmetries that we have found by now. And then we're going to really shortly take a look on how to apply those flavor symmetries. Okay, so let's start with the string setup. So my theory of choice would be the heterotic string theory, and we compactify the extra dimensions on toroidal orbifolds. This is a toroidal orbifold, for example. And for now, we're only doing a two-dimensional compact space, but we can simply work our way up to a 6-dimensional space by this like building block principle. Okay. So what is a toroidal orbifold? For this, let me start with a continuous space-time like R2, so 2 dimensions. What we can do is we take this continuous space-time and mod out some lattice lambda. So we will get a torus, or equally said, this fundamental domain over here in this lattice. And then, so this would be a torus, and to make a toroidal orbifold out of it, we can furthermore divide this torus by a so-called point group. So we took the continuous spacetime and divided it by the full space group, which is the point group and the lattice. So this is the space group, point group and lattice. And thereby we shrink the fundamental domain again by, for example, this picture over here. So then this would be the fundamental domain. And we gain those singularities, so in this case, 3 singularities, x, y, and z. Okay, and now you might ask, how can strings live on those orbifolds? And since we're doing heterotic string theory, we only have closed strings, and now closed strings always have a boundary condition. Now, because we are on an orbifold, in these extra dimensions, the strings cannot close only up like trivially, the usual boundary condition, but they can also close up to a space group element. So up to G, which is a space group element. And therefore, so physically distinct types of strings are characterized by their constructing element G, or better said, the different types. So one different type is corresponds to one conjugacy class of this space group G. So the conjugacy classes of the space group give rise to the different types of strings. For example, here we have this. This is a Z3 orbifold. We'll come to that later. This space group, the space group of this orbifold has, in the first twisted sector, 3 conjugacy classes, and one is associated to the string, which is localized at that singularity x. The other conjugacy class at y, and the third conjugacy class at z. And of course, I can now change those, which will give rise to a flavor symmetry, but I'm getting ahead of myself. So how to get a flavor symmetry? And this, or for explaining that, I want to start with an analogy. Namely, in our 4-dimensional world, so we know that the fundamental particle states are built from representations of the proper Poincare group. And we also know that the CP and T transformations, so charge, conjugation, parity, and time reversal, they can interchange those representations and therefore always the conjugacy classes simultaneously. And well, this is because CP and T are orthomorphisms of the proper Poincare group. An orthomorphism is a map from the group onto itself. So you can think of it more or less as a symmetry of the group if you want. So what we do now in our extra dimensions, and there we just heard that different types of strings correspond to the conjugacy classes of the space group. And what we could do is we calculate the outer orthomorphisms of the space group. And well, so orthomorphisms, they will interchange representations and conjugacy classes. And since our different types of strings correspond to the conjugacy classes, they will interchange our strings or our different types of strings. And we will then interpret these orthomorphisms as the flavor transformations. So very roughly said, you could say that the CPT transformations of the extra dimensions give rise to flavor symmetry, if you like. Okay, then we come to my next slide. So the next slide is about the Narain construction. And this is, so we find that the binding and close-decline momenta of one particular string, they lie in a Narain lattice. So this was a lattice of signature. If you have two dimensions for the right mover and 2 dimensions for the left mover. So this lattice has 2.2 signature. And it is really important that we consider this Narain lattice instead of the usual like target space lattice, of the usual 2-dimensional lattice, because this Narain lattice has 2 moduli. It has the complex structure modulus and the Kähler modulus. So the complex structure modulus just is a purely geometrical thing. So if you have 2 dimensions, you can have or if you have a torus, let's say like that, a 2-dimensional torus, you always have this complex structure modulus. But if you take the Narain construction, you also get this Kähler modulus, which contains the B field, for example, here, the Capromont background field, which is, of course, important. You don't want to miss this. And this is why you should do a Narain lattice instead of a usual 2-dimensional lattice. Okay. And yeah, so during your string theory course, or during my string theory course, I somehow heard that the symmetry of a Narain torus is given by those ODDZ symmetry groups. So for 2 dimensions, this would be O22Z, which has, so we have one SL2Z here for the complex structure modulus. We have another SL2Z here for the Kähler modulus. And we have a Z2, which will somehow correspond to a CP type of symmetry. And we also find a mirror symmetry because we have 2 moduli, and we can then interchange those 2 moduli, so this makes sense. And yeah, so this dividing by Z2 is because the negative identity matrix of this SL2Z has to be the same as the negative identity matrix on this SL2Z. So they're identified. This is why we divide by Z2. Okay. Now, I'm always talking about tori and lattices. Now we want to do orbifolds. And if we do an orbifold, we will take only those elements of this ODD, so O22Z, that will commute with the orbifold action, which would be the point group. So then this group is furthermore shrinked. For example, for the Z3 orbifold, the orbifold that we looked at the whole time now, there the complex structure modulus is fixed, so this SL2Z gets broken, and what will be left is this SL2Z and this CP type of symmetry. So doing an orbifold, you can break this O22Z symmetry, or only there's only some elements left of it. Okay, so now that we know how to more or less get a flavor symmetry, let's take a look on what are possible flavor symmetries, or what flavor symmetries do we find. And there we do find more or less 2 types of flavor symmetries. So we find the modular symmetries, which is kind of new. And we find those, I would like to call them traditional flavor symmetries, because they have been around for quite some time now. And yeah, we're going to first take a look at modular symmetries, and after that to traditional flavor symmetries. Okay, so the modular flavor symmetries. You remember the symmetry of the Narain torus was this O22Z group. And so for the Narain orbifold, we have this subgroup over here. And so the interesting part is that we find that the twisted string states, which will be the massless string states, so the ones that we're interested in our low energy effective theory, those strings, well, they transform trivially up to the orthomorphic factor, but trivially under this principal congruent subgroup of the SL2Z, so of the parts here from your modular group. But they do transform in a non-trivial representation under well, the quotient of those two groups. So let's take a look here. We had those strings X, Y, and Z. And under some modular transformation, little gamma here, they will get this, first of all, orthomorphic factor. They always get this. But they also get this non-trivial representation over here, this little row. And this is a representation of this quotient group. And this is a finite mod. So we would call this quotient group then the finite modular flavor symmetry. And then, yeah, of course, back to the strings. So let's say the most difficulty that we're dealing is finding out this row matrices, and this is not that easy. But I don't want to go into the details of these calculational difficulties. So let's take a look at what kind of finite flavor symmetries, finite modular flavor symmetries are there, maybe by now, or what are some examples for that. So for different n's here, we can have n's 2, 3, 4, 5, and of course this goes down. We have the quotient groups, so the primed and the not primed, so they correspond to either you take an SL2Z or a PSL2Z. So for the unprimed, you would take a PSL. And yeah, you find those symmetry groups like S3, A4, S4, A4, or even T prime. And now for our Z3 Narain orbifold, this means we find that our twisted string states transform under a gamma 3 in brackets 3, which means that we have this finite modular flavor symmetry, gamma prime little 3, which would be here T prime. So this SL2Z, or let's say the twisted states do not transform under the full SL2Z, so they do transform into full SL2Z, but trivially up to the orthomorphic factor. But they transform non-trivially in this gamma 3 here, which would be then the finite modular flavor group. Okay. Now, those were the modular symmetries. Now, the traditional flavor symmetries. So in our case here, when we calculate the orthomorphisms of the Narain space group, we find some sort of symmetries that do not affect the moduli. So that do not affect the moduli. And these we can interpret as the traditional flavor symmetries, which have been around for quite some time. So in this case, we find some translations in the Kaluza-Klein number. We find a translation in the winding number, for example, or even a 180-degree rotation. And we can look on how our strings act. So if we do this translation in the Kaluza-Klein number, what happens to our string states? And we will see that those X, Y, and Z string states, they will just get faces. Here we see that they will get interchanged into another here as well. So we see that those two, for example, give rise to an S3. We will call it a geometrical symmetry, and we can interpret those as the string selection rules. And the multiplet closure of those two groups will then give you another group, which is called delta 54. And this would then be the traditional flavor symmetry of our Z3 overfold. I've always been talking about the Z3 overfold by now. Okay. Yeah, so maybe one work I want to mention. So the traditional flavor symmetries have been classified for all orbifold types that give you an MSSM-like spectrum here in 2018. And I imagine that there has been a lot of work. So it's good that we now have all traditional flavor symmetries of MSSM-like spectra. Okay, so what have we found by now? So I told you we were looking at the two-dimensional symmetries. And by now we've always been discussing this Z3 orbifold over here. And we found the traditional flavor symmetry delta 54, and we found the modular flavor symmetry T prime divided by, well, not divided, times Z2. This was the CP type Z2. Of course, there are other two-dimensional orbifolds. So there's, for example, the T2 over Z2 orbifold. And there are 14 more, if you don't count the trivial torus. 14 more orbifolds to go, so there is still work to do in terms of classification of the two-dimensional orbifolds. So for the Z2 orbifold, for example, so there the shape is not really fixed, so we can have something like this pillow or this pyramid, I guess, or any shape in between those two. And well, we will have a traditional flavor symmetry of d8 times d8 divided by Z2, or d4 times d4 if you want. So we take the dihedral group which has eight elements. And we'd have a modular symmetry, S3 times S3 times Z4. So for this Z3 orbifold, the shape is fully fixed. This was because the complex structure modulus was fixed. But for the Z2 orbifold, for example, the complex structure modulus is not fixed, and this is why we can have those different shapes. And therefore, we find that the twisted states, so the for us massless states in our spectrum, the full SL2Z gets broken to this finite modular group S3 for the Kähler modulus and S3 for the complex structure modulus. Here we only have the Kähler modulus. And this Z4 would be the mirror symmetry over here. Okay, so you see we always have this traditional and modular, and of course we can combine them, but before that I totally forgot about the representations. So if you're doing model building, you would be always interested in the irreducible representations of your flavor symmetries. And for example, here for delta 54, we find a three-dimensional representation, which is of course very good if you want to describe a three-generation model. And yeah, for these Z2 orbifold, we find a four-dimensional irreducible representation, but there's still a lot of stuff you can do, like turning on Wilson lines, for example, or even considering six-dimensional orbifolds, for example, if you want to do a realistic scenario. So, okay. Now, traditional and modular. There's always traditional and modular, and of course, we can combine them. And so the combination of those two would be called an eclectic flavor symmetry. Now, you might wonder why I didn't write a direct product over here. This is because those two groups, they do not commute with each other. And this gives rise to a nice structure, or at least a very constrained structure. Namely, the traditional flavor group has to be a normal subgroup of this full eclectic flavor group. And the modular flavor group can only consist of outer orthomorphisms of this traditional flavor group. So this, let's say, setup is really, really constrained. Okay, so the last step is, of course, when we look at physics at the energy scales that are now available, we do not really see this symmetry, so it has to be broken somehow. And well, therefore, the traditional flavor symmetry, we can break this by, for example, introducing flavons. And the modular symmetry, that would be breaking by giving a BEF to the modulus, for example. So you might think of, if you are able to stabilize the modulus by some method. We haven't been considering methods for, or constructions for modular stabilization here. But for example, if you find a method to stabilize the modulus, so assign a VAF to this modulus, the modular symmetry will get broken. But what might be is that it does not get broken completely down, but there is still a remnant left, and this remnant will act like linearly. So what you can do is draw a map in the flavor space, so imaginary and real part of your modulus. And depending on the VEF, so choosing a VEF, you would be on some point in this plot. And depending on this point, you will find different remnant linearly realized flavor symmetries. We're again in this Z3 example. So whenever you're like some non-special place, you will find, so the modular symmetry is broken completely. So we only have the traditional flavor symmetry, delta 54 left. But if we are on some special cases, like for example, the fixed points of the SL2Z, or even for the CP-like symmetries on some of those black lines. So on all those black lines, we would have an enhanced linearly realized flavor symmetry. of, for example, this group, which I call 108 and 17. So this refers to the small groups library of GAP. So 108 is the order of the group, and 17 is just a consecutive numbering. Yeah, and we also find flavor groups of order 216 and 324. So those will be the remnant linearly realized flavor symmetries that we can get if we have a T2 of Z2 orbifold. Of course, we can also draw the same picture for the Z2 orbifold, but I thought it won't be a lot of insight in that. A thing that I wanted to mention is, so from 54 to 108, it's a factor 2. And this is because on all those black lines, the T prime finite modular symmetry gets broken completely, but the CP like Z2 symmetry, this is the one that does not get broken. So you can more or less say that you have this delta 54 flavor symmetry and you enhance it by a Z2 CP like symmetry if you are on those black lines. So if you have assigned the F of the modulus to some value, which lies here on these black lines. Okay. Now we saw what kind of flavor symmetries we found by now. And now let's take a really quick look in how to apply those flavor symmetries. So more or less what are bottom-up building model builders up to. And there has been a lot of development. So it all started with this paper by Ferruglio 3 years ago, a bit more than 3 years ago. And so it started with an idea, and if I want to say this full construction and bring it down to only one sentence, I would say that he uses modular forms as couplings in the superpotential instead of just plain constants or just plain numbers. And therefore, the Maus matrices for neutrinos, leptons, quarks, whatever, you find they contain those modular forms, and this is where he got this catchy title from, are neutrino masses modular forms. What you would then do is you would of course have to assign a specific value to the modulus, so you have to give a F to the modulus, let's say it like that. And they choose this specific value just so that it fits the experimental values very good. So for example, this is just some example plot to give you a rough idea. So there the best fit value would lie somewhere here. So what they would do then is say that, okay, we should give a F to the modulus, which is exactly this. So they're not considering any moduli stabilization mechanism or anything like that. Okay, so the cool thing about this approach with those finite modular symmetries is that it can be very predictive. Like for example, in just the first model that he proposed, he was able to get to predict 7 parameters out of the 2 parameters. So the 2 were the real and the imaginary part of the modulus. And he was able to give me 7 observables, of which 5 are experimentally measurable. So these can be very predictive. And this is of course nice if you want to do model building. Okay. Yeah, so I think I was fast, but coming to my conclusions. Hopefully you remembered that flavor symmetries can arise from orthomorphisms of the Narain space group. What we find then, if we apply this method here, is that modular symmetries as well as traditional flavor symmetries, we find modular as well as traditional flavor symmetries, and we can combine these to, we would call it an eclectic flavor symmetry. Now, those modular symmetries can be very predictive, and if you consider those eclectic flavor symmetries, then it is even more constraining. Bottom-up model builders have by now not considered these eclectic flavor symmetries, but I suspect that we will see that very soon. And yes, so I think we can say that string theory can provide some insights for bottom-up model building. And yeah, thank you.
Thanks for the very nice talk, Alex. Let's all thank him for his talk. And are there any questions?
I have one.
I'm not sure who came in under the wire, but Shreya?
Yes.
Shubha?
Yes. Yeah. So since eclectic flavor symmetries are very constraining when you are predicting neutrino masses, like the paper you were talking about, or neutrino masses modular forms, don't you effectively, like, you have one parameter here, right? Is that very constraining when you're trying to predict neutrino masses, because this is already pretty constrained as it seems to me?
It is already pretty constraining. So before those modular symmetries were there, you would only have those traditional flavor symmetries, which get broken by the flavons.
Right.
And yeah, so there is you'd have to align those flavons, the vefs of the flavons, very cleverly, and there's a lot of opportunity to have those vefs. And this always, and then still there is the exact value of the vacuum expectation value left. So there are usually a lot of parameters that you can play with.
I see. I have just one more question. When you were talking about modular symmetries, you said that the representation rho of gamma is very hard to find out. Do you like, why is that?
Yeah, of course. Let me just go back to the slide. This was this slide over here.
Yes.
Yes. So so what we find here is this O22Z. This is what we have. So we know how the Kaluza-Klein momenta and the winding momenta transform under this transformation. So how they change.
Okay.
But there's still the states left. So so your state depends on the Kaluza-Klein and the winding number.
Mm-hmm.
You know how the Kaluza-Klein and the winding number transform, but you do not know how the state transforms, because you have to. So what you would usually do is you write down the vertex operator for this type of string.
Okay.
And the difficulty is that we do not have the exact form of the vertex operator, at least for twisted strings, in our setup. We do have them for those winded strings, so the untwisted strings. And when we have some operator product expansions between those untwisted and the twisted strings, which then enables us that we can get the transformation of the twisted strings out of these OPEs where we only have untwisted strings.
Mm-hmm.
And so this is the difficulty, more or less.
I see. Okay, thank you so much.
Thank you for the question.
So let's take Paul, then Ling, and then Koa, and then we'll have to move on.
Yeah, hi there. Yeah, thank you for the nice talk. I have a quick question. So the first one is, so when you construct this Narain orbifold, do you then just analyze the theory in 8 dimensions, or do you complete it to a 4-dimensional orbifold in the construction with like regular orbifolds, or how do you, in which dimension does this happen, the analysis?
Mm-hmm. So we're considering let's say 2 compact dimensions, so 2 target space compact dimensions. But where our calculations are in is always 4-dimensional, 2 for the left, 2 for the left. So we are working in this Narain construction, but this is not the same as if you just take a 4-dimensional orbifold, because you still have this the signature of the Narain lattice. So you still have the Narain metric, which has to be preserved. And this is more or less the difference between the 4-dimensional orbifolds and our 2-dimensional Narain orbifolds, which are, of course, effectively 4-dimensional.
Okay, so this, and then also just one quick question. So the congruent subgroups that you're getting, are they always of gamma n type, or can they also be of gamma 1 or gamma not n type?
So if you do not consider Wilson lines, if you just do the usual orbifolds, you will always, so we have by now only found those gamma in brackets n type, but I surely expect that there can be gamma 1, gamma naught, or any other type of modular forms. also of congruent subgroups, and therefore, of course, of modular forms that you will have in your bottom-up construction. Just some days now, ago, the bottom-up people came up with those Siegel modular forms, for example, where you have, so for example, here you have multiple modular symmetries. And so you have multiple moduli, let's say like that, you have multiple moduli, and then you would have a subgroup of multiple moduli, and those, this is what Siegel modular forms, for example, are then modular forms of a modular group which has here multiple moduli, for example. And yeah, so we're really looking forward into Wilson lines and seeing what comes out there.
Okay.
Yes.
Great, cool, thanks.
And then Koa.
Hi. So I have a question. So you said earlier that the fitting for the neutrino masses are very constrained. So I wonder if you take into account of like the experimental data from the quarks and the leptons, is there any way that you can make the theory predictive?
Yes. So there have been, I think, a couple of models by now which consider not only the lepton sector, but the quark sector as well. So quarks, leptons, and of course the neutrinos as well. So the first model that came up, they considered a modular symmetry, but of course when you do the tensor products, you can have several trivial singlets, and then you get more and more parameters that you still have inside your theory. And I think, so this is a way where you can easily catch up parameters. And so I think by now, the model builders that considered quarks, leptons, and neutrinos, they had more parameters when they did this modular symmetry approach than the parameters that they predicted. So more parameters than they would be able to predict. But I suspect that you can do this in a more minimal way, where you have less parameters.
I see. Thank you very much.
Great. Well, let's thank Alex for his very nice talk again, and then we'll move on.